Hi folks, this is Miss Belsick. We're going to continue talking about the intro to logarithms. That very first lesson, these notes will kind of talk about slides 1 through 6 I thought it was out of 14, but it's actually out of 15. So it talks about the information in the first 5 to 6 slides. I think that 6th slide is introducing the stuff that's happening later. So it starts out talking about logarithms as an inverse. So remember inverses? You should know two basic things about inverses. So in general, inverses, we should know two things about them. So the first thing that we should remember about inverses is to get an equation's inverse, you have to switch the x and y variable and solve for the new y. So let's take let's see, switch x and y. So let's take the example y equals 2x, a linear function because there's no exponent. So we have y equals 2 times x. And if I were going to talk about the inverse, I would switch x and y's position. So this y equals would become an x equals, and this 2x would become a 2y. And now I just want to solve. I want to solve for this y right here. So right now they're being multiplied. The inverse operation is to divide by 2. That way 2 divided by 2 becomes 1y. And I get x divided by 2. And so this is the inverse, and I say it's the inverse by putting this little, kind of looks like an exponent there. So that's the inverse of my original y. So that's one thing that you need to remember about an inverse is in order to get an equation's inverse, you have to switch x and y. And it also makes sense here because the inverse of multiplying by 2 is dividing by 2, so that kind of makes sense. The next thing that we need to remember about inverses is that on a graph, inverses are reflected over the diagonal line y equals x. So inverses are reflected over the diagonal line y equals x. So let's talk about another pair of inverses, and then we'll graph them and you'll see this diagonal line y equals x and you'll see the reflection. So for an example, let's talk about y equals x squared. This is the quadratic parent function. There's no fancy anything extra. There's just y equals x to the power of 2. So it's the quadratic parent function. If I were going to talk about its inverse, what would I do? I would switch x and y and I would solve for the y value. So y equals becomes x equals, and x squared becomes y squared. And in order to solve, undoing a square means that you square root both sides. So that is gone, and I have y equals. Anytime you square root something, you always have the plus or minus, positive or negative value of it. And to denote that this is the inverse of the original function, or the original equation, I would give it this little, kind of looks like an exponent. Okay, so I'm going to move this up a little bit. There we go. So if I graph these, and I'm just going to sketch them, I'm going to try and sketch them nicely since this is, going out to everybody. So if I sketch the quadratic parent function, the shape is a what? A parabola with a vertex at 0, 0. And if I were plotting this, if I weren't sketching, if I were actually plotting this nicely on graph paper, which I don't have, so maybe I'll see if I can order some. If I were plotting this, I would use the quadratic pattern, which is over 1 up 1, over 1 up 3, over 1 up 5, over 1 up 7, and so on. But because I don't have graph paper, I'm going to sketch. That looks pretty good. And then if I were going to draw the inverse, which is the square root of x, the positive square root of x and the negative square root of x. If you remember what that graph looks like, it also has a vertex at 0, 0, and it looks like parabola kind of laying on its side. So notice that we have the line y equals x, that diagonal line right here, going all the way through, and we have some points that are occurring on this point right here is on both of my functions. This point right here, if I reflect across, occurs on its inverse. This point right here, if I reflect across, occurs on the inverse. So we've got some kind of reflected points here. And in general, any point for the line or for the parabola y equals x squared, any point a comma b will show up on the inverse function. Whoops, sorry. Trying to write quickly. Any point on the function will show up on the inverse function as b comma a. So what do you notice? The a and the b values, or here the x and the y values, are just switched. Okay, so that's just kind of a review about inverses, because you're going to need that whenever he talks about logarithms, because he starts out the video by saying that that logarithms are the inverse to exponentials. So I'm going to draw my little line here. There we go. Logarithms are inverses of exponentials. So remember the two things about inverses that we talked about. So you have to switch x and y, and on a graph, inverses are reflected over that diagonal line y equals x. So those are two ways that you can show a relationship between logarithms and exponentials because they're inverses of each other. So the definition that he gives you is that a logarithm, this is my key term right here, a logarithm is the exponent, this is important, logarithm is the exponent of a base that gives a certain value. So let's say we have a base of 5 and we raise it to an exponent of 2. 5 to the power of 2 is 5 times 5. That's 25. That's the certain value that we're talking about. So 5 to the power of 2 gives 25. And that certain value that he has in his definition, that value is referred to by the teacher as the argument. So when he talks about the argument, he's not talking about like an argument that people have. He's talking about the value when you raise a base to a power. So that's what he's talking about. So let's kind of break down what this looks like. If I had a base, here's my base. Remember, base is a large, either variable or a number. And I raise it to the power of a. That's my power or my exponent. Whatever I get when I evaluate that base raised to the power of this exponent is some answer. But what does the teacher call it? The teacher calls it the argument. It's just the answer. And remember how we talked about logarithms and exponentials being inverses of each other? If I said that y equals a base to a power, and I were trying to find the inverse of this, that means I would switch x and y. So instead of y equals, I would have x equals. And instead of b to the power of x, I would have b to the power of y. And I'd try to solve this, but there's no mathematical way that we know of to undo raising something to a power. Like I can't just multiply this power by its inverse. Like I can't raise it to the power of 1 over y. That's not going to work. So how in the world do I get this to go away? Well, the way you do that is you apply this new mathematical function that we've learned, and you take the log. So we would end up with the inverse being the log of b to the power of x. And something that I want you to notice, because it occurs in his problems, like the extra problems that he gives in his lesson, notice that this right here and this right here are the same. So if you're ever given a logarithmic function and you're asked to find its inverse is always this right here. For example, and this is just extra, let's say that I have the log of 5 to the power of x. That's my function. If I were trying to find the inverse, sorry, I should have written this over here. If I were trying to find the inverse would be this, 5 to the power of x. So just little extra pieces of information that I feel like are not there in the videos, but you probably would benefit from knowing. So let's do some examples. Sometimes, let's see. So he gives you an example, I think it's log, I think his example looks like this, right? So I'm trying to figure out, this is my unknown, like I don't know what this is. So I'm trying to rewrite this and figure out 2 to the power of what equals 8? Well, 2 times 2 is 4, times another 2 is 8. So there's 3 2's here, that means 2 to the power of 3 is 8. And the argument is 8, sorry. The exponent is 3. So I believe that's the example that he gives you. But I want to give you some other examples to work off of. So this is example 1. Let's talk about example 2. Ms. Belsick's example 2. So let's just talk about the pieces. I'm going to have this as my example. And by the way, if I were going to state this, like if I were actually going to say it to my friends, I would say it as log base 2 of 16 equals 4 or is 4. So log base 2 of 16. Log base 2 of 16. So that kind of reminds us that this is the base. So if I were going to, talk about my pieces of this logarithmic function, I would say that the base is 2. The exponent is what? Remember that a logarithm is an exponent. So the log of something is an exponent. So the exponent is 4. And then the argument is 16. Because base 2 to the power of 4, the exponent, is equal to the argument, which is 16. So it's kind of identifying all of the pieces. Let's talk about another example. Example 3. Example 3, I'm going to give you an unknown and see if you can identify what the unknown should be. So I have log base 3 of 9 equals x. So I want you to identify the base, the exponent, I'm going to abbreviate, and the argument, arg. Figure out what those are. So your base should be 3. Your exponent, that's what your logarithm equals, that's x, that's our unknown, and your argument is 9. So if you set that up as an equation, you should have 3 to the power of x equals 9. Well, what do I need to raise 3 to the power of in order to get 9? I need to raise 3 to the power of 2 to get 9. So what does my unknown equal? My unknown equals 2. Those are the basic way that you might be asked about logarithms. So I've got 2 more for you. So one example, and something that he talks about is that sometimes log base 10 of x is just written as log of x. So you're supposed to kind of understand that if there's no base written, it's a base of 10. So if I have log of 100 equals 2, well, what that means is that my base is actually hidden. My hidden base is 10, always. If there's no base that's written here, then my hidden base is 10. My exponent is 2. My argument is 100, which makes sense because my hidden base of 10 raised to my exponent of 2 equals the argument of 100. Just kind of an extra little thing that you might need to see an example of, something with a hidden base. So the last one that I want to talk about is an example with another unknown. So if you have log base 4 of x equals 3, identify the parts, base, exponent, argument. The base is 4, the exponent is 3. That's what the logarithm equals. The logarithm is an exponent. And the argument is the unknown. So if you rewrite this, 4 to the power of 3 equals the argument x. Well, what is 4 to the power of 3? It's 4 times itself 3 times. 4 times 4 is 16. And 16 times 4, hopefully you know that one, but if you don't, you should be able to use a calculator. 64. So my argument value is 64. Okay. So the next slide that the teacher has in Edgenuity is a really good visual of the inverse relationship between logarithms and exponentials. Remember that inverses switch x and y. Also remember, and I'm going to switch back in my notes. See if I can get that on the screen. Okay. So remember that if you have a point on your exponential function, a and b, then that shows up as a point on your inverse function, your logarithmic function, but just x and y switch. So instead of a comma b, it's b comma a. So remember that you have those reflected points on your logarithmic and your exponential functions. Okay, I'm going to try and get this in here. So on that next slide, what he talks about is how to graph logarithmic functions. So I'm going to pause the video for a second and I'm going to create my graph so that it looks nice and neat and I can show you what I'm talking about on it. Okay, so if you want to pause your video and take a moment to set it up the way that I have mine set up, I have a nice graph that goes to 4 and -4 in all directions. I also have a table set up with a process column, which is something that he does not show in Edgenuity, and so I thought you would benefit from seeing how we're getting those y values by hand. I know some of you might use a calculator that you've downloaded from your teacher onto your tablet, but you're welcome to follow along as we do it by hand as well. because it's important that you know how to do it by hand. So for the function y equals 2 to the power of x, if we're trying to create the y values, the teacher has picked these x values all around 0. And what we're going to do is raise 2 to the power of those x values. So here, 2 to the power of 2 is 4. So I would plot the point 2, 4. 2, 4. Next, I have a base 2, and I raise it to the power of 1. 2 to the power of 1 is 2. So I would plot the point 1, 2. 1, 2. Base 2 to the power of 0 is always 1, which is why we have the point 0, 1 always on here, unless we've done some kind of transformations to the exponential function. Next, I have base 2 to the power of -1. Now remember that when you have negative exponents, that moves your base and the exponent in the fraction, and it makes the exponent positive. So now this is 1/2, or in the video he has 0.5. So I'm going to graph the point -1, 1/2. And then finally I have base 2 to the power of -2, which again is 1 over the base to the power of the positive exponent, and that's 1/4. So I'm going to plot the point -2, 1/4, which is kind of an estimation. So this is what it looks like. This is my function, f of x equals 2 to the power of x. And what the professor talks about, or what the teacher talks about, is that whenever he graphs his logarithmic functions, he first graphs his exponentials, and then he reflects that function over the line y equals x, because we talked about how exponentials and logarithmic functions are inverses of each other. So they can be graphed by reflecting across the line y equals x. So this is y equals x, the line that you can reflect across for inverses. And so if I reflect across, I'm going to reflect in a different color. I can find a different color on my desk. There we go. So if I reflect across, this point becomes this point. Let's see, over 1 up 2 becomes over 2 up 1. Over 1, 2, 3. Let's see, is that right? Oh no, this is right here. Okay, so over 1, 2, and up 1, 2, 3, 4 becomes over 1, 2, 3, 4, and up 1, 2. This point, back 1 and up 1/2 becomes down 1 and over 1/2. Oh, sorry, down 1 and over 1/2. And then left 2 up 1/4 becomes down 2 and right 1/4. So here's my logarithmic function. And this is the inverse. It's log base 2 of x. So if I were going to go ahead and write my table for my logarithmic function, log base 2 of x, remember 2x, 2x, logarithmic, inverse that's exponential. If I were writing my points, my ordered pairs, I would just write the x's and the y's, but I would switch them. So my x's are now my y's, -2, -1, 0, 1, 2, and my y's are now my x's, 1/4, 1/2, 1, 2, and 4. So those are now my points for my logarithmic function. So that's the first half of his video. on the intro to logarithmic functions. I'll try and post another video soon. So until then, email me with questions or join my Zoom every day. Bye.